Welcome back. We have been discussing Fourier series, which is used for periodic signals, and we have discussed it for the continuous time case. Now, Fourier series, it is defined only for periodic signals, right? And it kind of gives you an insight in the frequency domain. You have a signal x of t, you compute the coefficients a of k from this signal, then you express this signal in terms of these coefficients, and that's kind of a frequency representation. Right? We represent a signal in terms of its harmonics. Normally these are we started a discussion of Fourier series that we're going to express x of t in terms of complex exponential signal, and complex exponential signal it involves a frequency parameter. But what happens if your signal is not periodic? There are a lot of, in fact, most of our real-time signals, they're not periodic. You can approximately say that they are periodic, but जो इनका inherent behavior होता है, it is that of non-periodic. So for that, we define the Fourier transform. Now we could just directly go to the Fourier transform, see what the equations are, but we would like to do a bit of analysis first. We will do a bit of mathematical analysis, and through that analysis we'll try to reach to Fourier transform. छोटा सा analysis करेंगे हम. So if I assume that that x of t, now I am dealing with non-periodic signals. So let me assume that x of t, it is a non-periodic signal of some finite duration. Fine. So let me take a typical case. Okay, I have a typical case like this. And this signal is something like this. It's a kind of a triangular pulse like this, right? So x of t, then this is the time t, and let's suppose it ranges from minus t1 to t1. Okay, so this is basically a signal x of t which is 0 outside this range. यहाँ से भी 0 है, यहाँ से भी 0 है. Right? Now it's not repeating. Signal repeat नहीं हो रहा है, so it's a typical non-periodic signal of finite duration. Right? Now from this I will try to construct a periodic signal. So what I will do, I will construct a signal, let's call it x subscript t naught t. Let this be a periodic signal which is formed by repeating x of t, and will ensure that it has a fundamental period t naught. Right? So it will be something like this. Okay, we have started from here, so this is my signal, and I'm repeating it multiple times with a fundamental this. Okay, if I choose an instant here like this on both sides, then I will repeat it on both sides like this, then another triangular pulse, this same thing. Have I done it right? नहीं, थोड़ा गड़बड़ थे, एक second. It should be actually up to this, then this. Similarly here, from here, this. Then I can continue like this, go up to this point, come down here, another period, like this side also. Okay, so this is a new signal that I have constructed, and this is x of subscript t naught of t, and it is basically a repetition of this signal, a periodic non-periodic signal. And here is my time period. Is extends from this point, this is one period, up to this point, so this has to be t naught. Fine, so let me, okay, this point is already defined, minus t1, this is 0, this is t1, so let me define this as minus t naught by 2 and this as t naught by 2. Fine, so this is centered about 0. So if I continue like this, then this obviously will be t naught, this will be twice t naught, and we can continue likewise. Similarly here it will be minus t naught minus twice t naught, and so on. The thing is that this signal is a repetition of this non-periodic signal, okay, and with a period t naught. Okay. Now if I put a limiting case that if we let t naught to go to infinity, which means graphically ये जो ये वाला point है t naught, it goes to infinity, and this also goes to infinity, और आपका जो period है which is t naught, it will become infinity, which will be typically you will get this signal, क्योंकि इसमें भी you have a single pulse, इसमें भी आपको फिर एक ही rectangular pulse होगा, जो बाकी होंगे because I'm putting a limit की period should be infinity, so they will be located at infinite. Apparently it will seem on a real time scale that you only have a single pulse, बाकी सब minus infinity or plus infinity पे है, which means they're not there. Okay, just for mathematical analysis. So if this is, if t naught tends to infinity, we can say that limit t naught tends to infinity, x of t naught t is actually x of t. Just try to understand this. I'm giving you both mathematical form as well as this graphical representation. So in other words, I am relating a periodic signal with a non-periodic signal through the condition that time period is infinity. Means आप ये कह सकते हैं कि a non-periodic signal is periodic with an infinite time period. This is just a pictorial representation. Single pulse, non-periodic. I have repeated it multiple times to get a new periodic signal. Then I have put a condition on this periodic signal, it has an infinite time period, which means all these from here to this on this side and from here to this side, they will go to infinite, minus infinity and plus infinity, which means on a realistic time scale you will be left with only with this pulse which was originally here. Okay, so based on this we'll try to expand our mathematical analysis here. Now x of t naught t, that is this signal, it is periodic. Fine. Now since it is periodic, which means we can apply Fourier series to this signal. So if I go for a Fourier series expansion, so if I go for Fourier series of x subscript t naught t, it will be like this, x t naught, जो हमारा है the synthesis equation that we have, that k runs from minus infinity to plus infinity. We have a coefficient a of k and then the exponential factor k omega naught t, where obviously omega naught is the fundamental frequency related like this in our particular case, because our time period is t naught. And then you have the analysis equation where you compute a of k as 1 upon t naught over the time period. Now time period here is t naught, but it is from minus t naught by 2 to plus t naught by 2. So if I proceed to limits minus t naught by 2 to capital T naught by 2, x of t naught t e raised power minus j k omega naught t with respect to time. So we have d of t. Now we have this limit from minus t naught by 2 to t naught by 2. So it means from here to here I am considering only this part. लेकिन इस range में the signal is quite similar to x of t, because you are only considering one period जिसमें I have a single triangular pulse which is also x of t. So I can say, I can make a substitution here that 1 upon t naught in the range minus t naught by 2 to capital T naught by 2, I can replace this thing by x of t. Fine. Now I have expressed this in terms of x of t. Then yet again I can do other another this and the kind of substitution. You see ये जो आपका signal है, so let me just, I have these two defining points minus t naught by 2 to t naught by 2. So जो मेरा पहला substitution था कि because my range is from minus t naught by 2 to t naught by 2, so I can very much replace this thing by this, because इस range में this and this is similar. The second substitution I can take is that instead of expressing it for the range minus t naught by 2 to t naught by 2, I can have actually minus infinity to plus infinity, because सिर्फ इस रेंज के लिए ये डिफाइन है, इसके बाहर इट इज़ ज़ीरो. ठीक है. So whether you write it like this या whether you write it like this doesn't matter. Now why I am doing it, I am trying to bring it in a particular form जहाँ से जाके फिर मैं I can express what my Fourier transform is, the general form. Okay? That's why I'm making these kind of substitutions. This, because इस limit में, इस time interval में, this waveform and this waveform is same. And then this minus infinity to plus infinity, because it doesn't matter. Minus t naught b to minus infinity and t naught to plus infinity. The signal is 0. आप ये limit लीजिए या ये limit लीजिए over x of t, that is, it is one and the same thing. So let's call it 1. Now let us define, now we are coming towards Fourier transform. So I am defining a new term, capital X omega, and I am defining it minus infinity to plus infinity x of t e raised power minus j omega t. Okay. Then you can very well express your coefficient a of k as, because our a of k is 1 by t naught, x of t e raised power j k omega naught t dt. अभी मैंने एक्सप्रेस किया. So a of k can be expressed as 1 of t naught, 1 by t naught, capital X k omega naught. ठीक है, because x of omega is this. If I take x of k omega naught, it will be minus infinity to plus infinity x of t e raised power minus j k omega naught. मतलब ये वाला term, ये वाला integral, and 1 by t naught तो बाहर है ही. ठीक है. Then coming back to x of t naught t, we know that it is k runs from minus infinity to plus infinity. This one, ये वाला, just a second. Right? तो इसी एक्सप्रेशन में अब a of k की जगह आपका ये है. So I will substitute 1 upon t naught x of k omega naught, then e raised power j k omega naught. All I have done is a k को मैंने substitute किया in this. Fine. Then again a bit of mathematical substitution. It's from minus infinity to infinity. T naught is equivalent to 2 pi by omega naught. So if you substitute here, it will be omega naught by 2 pi x of k omega naught e raised power j k omega naught t. Right? I can take 1 upon 2 pi outside. Sorry. internal summation will be from minus infinity to plus infinity, x of k omega naught e raised power j k omega naught t, and we also have this omega naught here, right? Now if I proceed to limits, so as t naught tends to infinity, it means omega naught, which is equivalent to 2 by t naught, will tend to 0. It will be a very small infinitesimal quantity. So under this condition, let us say that omega naught, because it will be touching 0, so it will be a very small quantity. Let's call it denoted by delta omega. Then x of t naught t, as t naught tends to infinity, that means proceeding to limits, it will be equivalent to 1 by 2 pi k runs from minus infinity to plus infinity, x of k delta omega e raised power j k delta omega t delta omega, जहाँ जहाँ पे omega naught है, since I'm proceeding t naught to infinity, I'm using the limits, तो जहाँ जहाँ पे omega naught है, it will tend to be delta omega. It will tend to go to 0, which means it will be a very small quantity. It will tend to delta, जो हमारा normal limits का concept है. Now we have already defined that x of t is equivalent to this, which means ये जो मेरा left hand side है, जहाँ पे I am taking the limits for this, I can say it is x of t. So x of t is limit t tends to infinity x of t naught t. Yeah, in other words, it is actually limit delta omega tends to 0 for this particular expression, 1 by 2 pi k is equal to minus infinity to infinity x of k delta omega e raised power j k delta omega t, then delta omega. Now it's a typical case of limits. Whenever this tends to 0, आपका summation, it becomes an integral. So x of t equivalent to 1 by 2 pi integral minus infinity to plus infinity x of omega e raised power j omega t d omega. Okay. And you can express x of omega as minus infinity to plus infinity x of t e raised power minus j omega t dt, जो ये था, this one, here we have defined this. So when we define x of omega like this, then it turns out that x of t can be expressed as 1 upon 2 pi minus infinity to plus infinity x of omega e raised power j omega t d omega. Okay, so together these two equations, that is this and this, they constitute Fourier transform pair. जो आपका equation 1 है, where we get x of omega from x of t, it is referred to as Fourier transform. And the second equation, where you get back x of t from x of omega, we call it inverse Fourier transform. Okay, so you will see that it's quite similar to Fourier series. Only difference is कि अब दोनों cases में integral है, because these are the limiting cases. Limiting in the sense we are expressing our periodic signal as a limiting case of our, sorry, we are expressing our non-periodic signal. If you go to the analysis from where we started, we are expressing a non-periodic signal as a limiting case of periodic signal. Limiting in the sense कि आपका जो period है, it tends to infinity, which in other words means कि आपका जो fundamental frequency है, it tends to 0. Okay? So this is the one basis Here we started, and then we did a bit of analysis, and we came up with the Fourier transform equation. Now if you can see, if you kind of compare it, there's a kind of a symmetry between series and Fourier transform. जो हमारा, where did it go? Here we also had a pair here, so x of t was as a summation of this. Then we computed coefficient using the integral. So you can say that a of k kind of is symmetric to your x of omega. Okay, so as a vague approximation, I can say that the coefficient in my Fourier series a of k, b of k, jo bhi ho, it kind of resembles the transform in my Fourier transform. Fine. So again, they form a pair. The equation 1 is Fourier transform, equation 2 is the inverse Fourier transform. So you may say, again, if we go back here, वहाँ पे we had synthesis and analysis equation. This was the analysis equation, so you may consider this as a Fourier transform, and this was your synthesis equation. You may kind of जैसे मैंने कहा, there is a symmetry, symmetrically के हिसाब से you may say this is the inverse Fourier transform. Okay, we'll stop here. There are some conditions with respect to Fourier transform. We'll take it next time, next class, next video.